Hello everyone. My name is Fuku and I'm a third year student at the University of Colorado. Today I'm going to talk about our research work on detecting the presence of the drone by identifying the physical signature of the drone by identification. This is my joint work with Andrew, Mahesh, Anthony, Professor Richmond, and my advisor, Professor Ken. Drone accident have reported increased. Last year, FAA reports hundreds of close calls between airplane and drones. Or in 2015, there was a drone crash that's very close to the White House, despite again verifying law in DC. Or 2 weeks ago, there was a drone crash that caused a power failure and evacuation in Matthan, California. So there are many drone accidents happened recently, but I would like to show you some examples of the accident, just for illustrating the very important and timely issue of designing a drone detection system. This is the first example. The drone crashed in the wing of the airplane. This is very simple. Or in the second example, the drone that flies through the window hit the human head while he's working in his office. And this is the most scary one. So, preventing the drone to fly in a restricted area is very important. So that's why there's so many effort has been done for taking down the drone. The first solution is what a drone defender. The idea is that the user simply fire a concentrated coil of energy that disrupts the RF communication and the GM reception of the drone, therefore bring down. Or we can use Skywall.
Skywall uses an advanced computer-aided visual targeting system that can track and bring down the moving drone from up to 100 yards away. When the system locks on, Skywall fires a capsule containing a huge net and a parachute. Once the drone is captured in the net, the parachute brings the drone down safely and intact.
Or we can use a very powerful drone to chase and bring down.
Hippo is equipped with an onboard camera and can be guided to intercept. Fire a net at the moving drone and disable its propellers. The net can be fired freely, causing the drone to drop to the earth like a stone. Or the net can also remain tethered to the Hippo, allowing it to carry its opponent back to base for examination.
Or interestingly, this is what's happening in Egypt.
These birds of prey are absolutely beautiful when seen up close. But after one look at one of these majestic creatures snatching a drone from the sky, and you'll know it's not their good looks that makes them so successful in the wild. So if you're flying a drone in the Netherlands, in a place where you shouldn't be, as they say in the airline industry, watch out for bird strikes.
Very interesting. But all of these systems and methods have the common assumption. The drone present is not detected, which is highly likely not the case because we need to detect the presence of the drone before we want to bring it down. So, talking about detecting the presence of the drone, there are some interesting technology to do that. The first one is acoustic-based signature. So the key idea here is try to detect the presence of the drone based on their acoustic signature. This work has been investigated by some companies like Drone Shield, Drone Detector, or the US Army Research Lab. The problem here is that the system performance is very dependent on the environment because it is very easy to be affected by the noise of the environment. So, and more interestingly, design engineering has invented a new technique to create a simple quiet drone techniques direction. The key idea is to create a frequency to cancel out the noise frequency of the drone. So this technique makes the acoustic-based signature drone detection useful. The second approach is to use video-based drone detection. This approach has been investigated since 2011 from some research lab and also from some company like Rifle or Matthan. But all of these systems require a very costly computing sensor hardware and a very high bandwidth of network connection to stream the video. More importantly, it can detect the drone with a very short range, around 50 meters maximum, and it requires a light offside condition between the detection system and the drone. And the performance of the detection system highly depends on the environment condition, the light condition of the environment. And it is really difficult to differentiate between the drone and the birds. Or more interestingly, drone can render invisible using new material technique invented by the CST. So this technique makes video-based drone detection useful. Or another technique is using radar-based approach. The key idea, the problem with this technique is it's very expensive and create a much interference to the environment. So we ask ourselves a question: can we detect the drone using the Wi-Fi example? And what is the benefit? What are the benefits of doing that? Is it very cost-effective? We can utilize the ubiquity of the Wi-Fi access point. And we can easily connect to the drone defense system using the internet. We present a drone detection system called Matthan. Matthan includes a Wi-Fi receiver that passively listens to the communication channel between the drone and the controller, and then explore the two physical phenomena of the drone movement in the received signal. The two physical phenomena here are the drone body shifting, which caused by the controller mechanism of the drone, and the body vibration, which caused by the propeller rotation. But in order to realize our system, there are many challenges preventing us from realizing our idea. The first challenge is that how can we differentiate between the signal from the drone and the signal from the mobile device and carried by the drone? Or how can we differentiate between the signal from the drone and the signal from the Wi-Fi access point inside the moving vehicle like a bus? Or the drone movement can happen with unpredictable patterns. How can we detect it? So here's the idea. Considering the scenario where the drone moves from balanced state to unbalanced state, as in this figure, and that scenario can happen by external impact, which is, for example, the wind condition, or it can happen by the internal impact from the error of the sensor reading or the imperfection of the propeller manufacturing. But there's a one component in the drone that can fix this problem, bring the drone go back to the balanced state. It's called controller mechanism. So the key idea is that the controller mechanism will control the propellers on the right side to create a force delta F1 to bring the drone go back to the normal state. But this solution cannot be solved, cannot finish in one iteration. It takes multiple iterations to actually bring the drone go back to the balanced state. If we block out the waveform movement of such event, it will be something similar like this. And if you pay attention into this waveform, you will see that it is very similar to a waveform. And in our literature, we know that if the event happens with the wavelet transform, with the wavelet form, we can detect it using the wavelet transform analysis. So the key idea here is we will detect the body movement of the drone using the wavelet transform analysis. We validated our idea by setting up the experiment as in the picture. We attached the wireless transmitter on the drone that emits 2.4 gigahertz signal, and we have a receiver on the other side that captures that emitting signal. And we also attach the IMU using the motion sensor to capture the motion of the drone. And then we plot the signal from both the IMU and the wireless receiver. We saw that whenever the drone creates a curve, it creates the event can be easily captured by both the IMU and the wireless data. So the conclusion here is that the drone movement modulates wireless signal that's sent from the transmitter. So the key idea is that if we can capture the signal sent by the drone, we can analyze the physical movement of the drone. So I mentioned before, the wrong body movement is very similar to the wavelet transform. We do some, we put the received signal that sent from the wrong and put it into a wavelet analysis, and this is the result. We see that the body shifting signature of the wrong is very easy to be detected. However, this is very difficult to use this signature or not to detect the wrong, because it may be very easy to confuse between the signal from the wrong and the signal from the Wi-Fi access point inside the box or the mobile device and carry money. So we need a more unique signature to detect the wrong body movement. It is the wrong body vibration. Considering the watt motor that has 4 propellers in the picture, we see that in order to move the rod from one place to another, the 4 propellers need to rotate at the speed omega 1, 2, 3, 4. Such mechanical control mechanism create the vibration on the entire body of the rod where the Wi-Fi card is placed on. So if we capture the signal from the Wi-Fi card placed on the rod, we can capture the vibration of the rod. And we capture the signal that's sent from the rod and put it into the energy analysis. We found that the body vibration of the rod can be easily identified. So the key takeaway here is that the second signature, which is the wrong body vibration, can be detected using a fast-forward techniques. We also validated our idea by attaching the ion field underneath the propeller of the rod and compare the data between the rod and the wavelet receiver. And we found that there is a very high correlation between the two data. So understanding the two physical signature of the drone movement, including the body shifting and body vibration, we put together a combined classifier. This combined classifier will eliminate the impact from the electromagnetic noise in the environment, and also eliminate the false alarm of the detection in the system. For more detail about this combined classifier, I refer you to the paper. We evaluated the system using the USRP P200 2.4 GHz directional antenna, and the frequency of the rod communication is identified by the Wi-Fi analyzer app. And we evaluated the system with 7 different types of rod, 3 different environments, urban, campus, and suburban, with the distance from 10 meters to 600 meters. And here's the result. For the 50 meter distance, we can detect the presence of 7 different types of rod with the accuracy up to 93.9%. And when we vary the distance from 10 meters to 600 meters, we can still obtain the accuracy of 84.9% accuracy. We test it with 3 different environments. We can obtain up to 96.7% accuracy with the suburban environment. And more interestingly, we also try to classify different types of rod based on the vibration frequency of the rod. The vibration frequency we obtain from the ion effect on the rod. And we can obtain up to 89.7% of accuracy for classification. For the future work, we would like to develop an automated channel sensing to identify the frequency of the rod communication inspired from the common integrated spectrum sensing. We also want to integrate an automated ceiling beamforming antenna to keep track of the rod. We also want to localize the rod and detect multiple rod at the same time. For conclusion, we introduced the system to detect the presence of the rod by analyzing the 2 physical signatures, the rod body shifting and the rod body vibration. The system obtained a high performance at different distance, different environment, and different time. For that, we